Welcome everyone. We're now into chapter 3 of the GD&T series. And in this video, we'll finally really start digging into ASME Y14.5 GD&T principles. As usual, if you're new to this series, I strongly recommend that you start from chapter 1, just so you don't feel lost or overwhelmed. Let's start with a really important concept that is introduced in GD&T, the concept of a feature of size. There are actually two types of feature of size. There's regular and there's irregular. I won't go into irregular features of size since they're a little bit more of an advanced topic. So for now, we're just going to stick to regular features of size. When you hear feature, you might think of something resulting from a CAD operation. And for the most part, you would be right. A fillet operation creates a feature. A hole is a feature. A feature is simply any physical portion of a part. So like a flat face or a hole or a cylindrical base. A feature of size more or less shifts the focus from what the shape is to how it is measured and constrained. So features of size are really important in GD&T as they allow us to apply certain geometric tolerances. So what is exactly a feature of size? A regular feature of size is a feature with two opposing points about a reference. So why two opposing points? It's so we can measure its size. You need 2 points to measure from. The general rule of thumb is if you have a pair of if you can measure it with a pair of calipers or a micrometer, and you're measuring across one feature, that's important, one feature, you have a feature of size. I put together this example using a picture of a dog. So obviously we know that dogs have ears, we know that dogs have a nose and feet. These are all features of the dog. But let me ask you this, can you measure the ears? Well, you can certainly measure parts of the ear, like its thickness, but you wouldn't really just be able to grab a pair of calipers and measure the overall size of the ear. There's no single dimension that fully represents the ear. That is one of the main differences between a feature and a feature of size. You could, for example, take a very large pair of calipers and measure the height of the dog. But that still wouldn't be a feature of size. Why? Well, that's where really part 2 of the regular features of size comes in. There needs to be two opposing points, we already know that, but about a reference. That is the important part. It's about a reference. That may not make a lot of sense right away, but for now, I would say it's best to think about it that if you're taking a dimension over multiple features, it isn't a feature of size. So here you could say the dimensions be taken from the feet to the legs up all the way up to the body. It's not a feature of size. And I put this for a demonstration here. You could take a pair of calipers and measure every single one of these individual, but not over multiple features. And that's really what makes it a feature of size. All right, so let's apply this principle to a real part. Which one of these features are features of size? We have the bottom surface, side surface, top surface, the hole diameter, the length of the block, the height of the block. Which ones are about measuring? Which ones aren't? Like which ones can you not inherently measure? You probably got it right. Only really the measurable parts are the feature of size. So that'd be the hole diameter, the length of the block, and the height of the block. And same as in the previous example, I put some virtual calipers to demonstrate the point. So going back now to the two opposing points about a reference, so the reference part of the definition, what does that look like? What does the reference mean? For each one of these, there's a virtual reference. It's an axis for the hole and midplanes for the other features of size. and for just to be clear, if you were measuring a sphere, which is also a feature of size, if you're measuring one, it would be a point. The important part is that the feature is identical from both, or if it's a plane, it's both sides of the reference, or if it's an axis, all sides. Same thing with the point. If it's identical from all sides, well, you got yourself a feature of size. This obviously wouldn't be true. It wouldn't be identical on all sides if we span a measurement across multiple features. The caliper teeth reach equally on all sides of the reference. So that's what allows it to be a regular feature of size. The next thing I want to introduce as part of GD&T is called the feature control frame. You likely saw it used in the previous chapters, but here I will formally introduce it. The feature control frame really has three compartments. At minimum, it has two. The first one is the geometric characteristic symbol. So what geometric tolerance do you want to apply? Those are from the list that I introduced in the first video. The second is the tolerance value. It's the value that controls the geometric tolerance. So how much do you want to control that tolerance? The last one, which is again is not always there, but it depends really on the specific geometric tolerance you apply. Some of them require them. Some of them require datums, which is what the last compartment is called. So yeah, it's for datums, and we'll dig into datums soon. And as a quick thing to note, feature control frames can be applied to both features and features of size. All right, so datums. Datums are one of the most important things in GD&T. In fact, they're critical. Where you place your datums really matters. So datums allow for relations to reference features. Generally, those reference features are called the datum features. Datums are used to establish they can be used to establish a sort of coordinate system. And that would be called that's called a datum reference frame. And this datum reference frame, so DRF, they're required for certain geometric characteristics, but not all. We'll dig into DRF soon. For now, let's look at an example that doesn't require a datum reference frame, or perhaps you could say it requires a partial DRF. For now, we'll just say it doesn't require DRF. The parallel characteristic is a really easy one to understand. We all know what parallelism is. We know what two parallel surfaces look like. They never intersect. So this is how you would set up a parallel tolerance, and you would use a datum. So you refer to the particular surface by giving the reference surface a datum feature symbol, and that's shown in red. And then you would reference the datum in your feature control frame. One thing I quickly forgot to mention, it is usually for the most important surfaces. You usually put datums on your most important surfaces, and it communicates design intent, but we'll get to that a little bit later. So here's how I would read this. This surface is parallel within this tolerance to this datum, which is this surface. So actually, in this particular case, pretty straightforward to read. A datum can be one of three things, or technically also a combination of these three things, of one of these three things. For now, let's simplify it. Let's just do one of these three things. The combination is much more advanced. So it can be a plane, an axis, or a sphere, and it really just depends on where you apply your datum feature. Your datum feature call out or flag or whatever it's called. And by the way, you'll notice that the dimension for the sphere contains an S before the diameter symbol. That indicates it's a sphere. All right, moving on. let's talk about datum reference frames. So I mentioned that it's like a coordinate system. The DRF is kind of like a coordinate system. It's usually 3D Cartesian, and it's typically established when a part is fixed in space. So that means all 6 degrees of freedom are constrained. So as a bit of a review, the 6 degrees of freedom are 3 rotation in each axis and 3 translation. Partial datum reference frames are also an option, but for now, let's just put that aside. Let's not go overcomplicate things. If you're familiar with linear algebra, I would say that one of the most common ways to establish a datum reference frame is to select 3 perpendicular surfaces, or 3 surfaces where their normal vectors are perpendicular to each other, or I guess you could say normal to each other. I find this very much like selecting an origin point and 3 basis vectors. But if that didn't make any sense to you, I came up with an example that should help understand intuitively what's going on. I find that for beginners, or at least for me, it was a little bit difficult to understand at first what a datum reference frame really even is. So I'll provide an example that might at first appear to be completely unrelated, but I promise you it'll make datum reference frames make so much more sense. So for what we have on the screen here, let's say you have a piece of wood on the left. You have this piece of wood, and you want to drill a hole in a very particular location of the part. And your tool of choice is a CNC router. So you can see here, this is a CNC router. Well, if you've ever used a CNC router before, you know that you first have to select your part orientation. So what orientation are you going to put the part in the router? And so that means, picking the direction you want to put the part in the machine. The bottom left corner of your part is usually the origin, so circled in red here. And it helps to select a corner that is a right angle. And on this part, I have 3 corners that have right angles, but I would really only say that 2 of them are good fits. So we're going to focus on these 2. The 2 highlighted in red. This one here and this one here. So which one of these 2 right angle corners do we want at the origin? Well, I don't know. Let's go through both of them. Here are both part orientations sitting on the work surface of the CNC router. You can see that the coordinate system relative to the part is different depending on its orientation. So the path that the CNC router would take, or the basis vectors that would dictate the path that the CNC router would take relative to the part is different. So here on the left, you can see I put some imaginary basis vectors, and they're different. So the location of the hole is defined in terms of the coordinate system, which can be seen with the blue, red, and green arrows. Yeah, and so again, if you're familiar with linear algebra terms, that would be the basis vectors. They're different relative to each feature of the part. Now, a CNC router wouldn't directly follow the blue, red, and green arrows. The actual tool path would probably look something like this and the purple, pink lines, just so the tool wouldn't collide with the part. Okay, so we've identified 2 potentially good orientations. We need that orientation to be fixed in place. Obviously, we can't start machining if it's free to float around. So let's imagine the wood was ferromagnetic, so like if it was made out of iron or steel. It's attracted to magnets, and now imagine that the part was in a zero gravity environment, and the coefficient of friction, so mu, between all the surfaces was 0. The part is completely free to flow off into space, and therefore is able to move along all 6 degrees of freedom. Now, where would you place magnets to restrict the movement of this part? Well, you'd probably focus on the biggest surface of the part first. We could put it on the top, but remember the hole is going to be drilled from the top. So let's just put it at the bottom of the part, which is the top of the router's work surface. This will be our primary surface. So these surfaces right here. So now we replace the surface with a big magnetic sheet. We still have a problem. So we constrain the rotation in the x and y directions, as well as the translation in the z directions, but we still have 3 degrees of freedom remaining. So where might we put more magnets to restrict the motion? And as you can see, the green and red arrows are still directions, and the blue arrow here for rotation, that's still how it can move. Well, we might focus on the next biggest surface, so a secondary surface. So one of these 2 surfaces here should probably do fine. So now we put a magnet there, and now there still remains 1 degree of freedom. So let's put up another magnet. So we'd probably put it here, the tertiary surface. All right, so now the part is sufficiently constrained. It shouldn't move at all while the CNC router drills a hole. Now, of course, if this was a real part in these conditions, the magnets would have to be strong enough to withstand the force. But let's assume the magnets are like infinitely strong. So without realizing it, you just establish a datum reference frame. Wherever you place your magnets, those are your datum features. So that's where you would put your datum feature symbols on those surfaces. These datum features sit along a theoretically perfect datum, and the datums fully constrain your parts 6 degrees of freedom. That's the important part. The surfaces themselves aren't perfect, of course. You can't have perfect surfaces. So they aren't the datums themselves. That's why we call them datum features. They sit along the datum. It's worth going over the 3-2-1 rule, although I'm pretty sure this only applies to 3 perpendicular datum features, so it's not universal. So we picked the primary surface, which you could say is the most important surface. That's often the largest surface. That constrains 3 degrees of freedom. The secondary surface is usually the second largest perpendicular surface, and that constrains 2 degrees of freedom. The last surface is perpendicular to both, and that constrains 1 degree of freedom. So that's why it's called the 3-2-1 rule. Because you constrain 3, and then you 2, and then 1 with the 3 perpendicular surfaces. By the way, if you were to take that CNC router and you were to give it a probe, you would basically have a CMM. And a CMM is a tool that you would use to inspect a machine part to see if it fits the tolerances in the drawing. That's a bit of an oversimplification. Of course, a CMM is technically a lot more complicated than that. But the coordinate system we just established for the router is basically the exact same coordinate system you'd use to inspect the part with the CMM. Datum reference frames don't have to be only established using surfaces. They can also be established using cylindrical features of size, or even spherical features, although I would say that's more of an advanced usage. A good example here is a random pin I drew up. It's clearly designed to fix something in place. So we want to select datums that communicate that design intent. The first and most important datum feature would be the shaft. It's clearly meant to slide into a hole of some kind, and so that would constrain 4 degrees of freedom. That would be 2 translation and 2 rotation. The underside of the hex head would probably be the second datum feature, because it looks like it's clearly meant to sit flush against a surface. Now you would know this as the engineer designing how it's to be used. So that's why you would pick that's how you would pick the datum features. You would know that it's meant to sit flush. So it's a main surface, so it's a great candidate for a datum. That constrains 1 degree of freedom, a translation, and the part is still technically free to rotate, to spin around the shaft's axis. For the last feature, there are two options. Both of these constrain the last degree of freedom, but the reason why I have them both here is because they both communicate very different things in terms of design intent. And I believe that one of them is far better than the other. If we were to select a surface along the hex head, it would communicate that the hex head surface is important. Maybe we would do that if we cared mostly about, I don't know, the width of the hex head or some other geometric tolerance relating to the hex head. But I don't think that is the case for this design. There's a hole for the retaining clip, and that is clearly more important than the hex head. It's also a mating surface because that's where the retaining clip mates through. So to be clear, that's this hole right here. So I would personally choose the retaining clip hole as a third datum feature. That's where communicating design intent is crucial. You often have to consider the function of your part when selecting datum features. There are technically many ways to establish a datum reference frame, but not all of them are good. The best ones help to communicate the design intent of the part. All right, so let's move on from datums and datum reference frames. A really critical concept that is used a lot in ASME Y14.5 is the concept of the maximum material condition and the least material condition. If we are to think of a hole in a part with a particular plus or minus tolerance, the maximum material condition, or MMC, would be the hole when it is at its smallest. It would be at its lower limit. The MMC is always when the part has the most material. It helps to consider the weight or mass of the part. So in the case of a hole, a smaller hole or a smaller diameter will cause the part to weigh more than a bigger hole would. You would remove less material with the drill bit, so more material would remain on the part. And it's the opposite for a pin or for an external feature. The smallest diameter would actually cause the part to weigh the least. So for an external feature to be at MMC, it would be at its largest diameter or its upper limit. And you can think about if you have a cylindrical feature on a lathe, the largest diameter is the one where you remove the least material. The least material condition, or LMC, is the opposite of the most material condition. It's when the part has the least amount of material. We can use weight here too to consider when a part feature is at LMC. A hole's diameter is at LMC when it's at its upper limit, and a pin or shaft's diameter is at LMC when it's at its lower limit. So now we're finally on to Rule 1 of ASME Y14.5. Rule 1 states that if a feature is at MMC, it must have perfect form. So what does that mean? Well, let's imagine we have a cylinder at MMC, so that means it's at the upper limit dimension. So if we had its diameter dimension at 10 millimeters, plus or minus 1 millimeter, the cylinder at MMC would be 11 millimeters. Let's imagine that cylinder at MMC is perfect, unrealistically perfect, down to the atomic level. An absolutely perfect 11 millimeter circular diameter. Perfectly round, the surface is perfectly smooth, everything. The surface of that perfect cylinder at MMC would form an envelope. It would be a perfect cylinder. The envelope would be a perfect cylinder at 11 millimeters, or at least for this particular example. It depends on the tolerances that are given. That envelope is a boundary that can never be crossed. It cannot be crossed when the part is at MMC, and it cannot be crossed when the part is at LMC. So obviously, that would mean that there's more tolerance for form deviation when you're closer to LMC. This rule can change with certain modifier and even certain geometric characteristics, and we'll dig into that later. But for now, assume that rule 1 always applies. This comes by default with ASME Y14.5. So even if you don't put anything else on the drawing, if you put the notes, dimensioning and tolerancing shall be in accordance with ASME Y14.5 2018 on your drawings, even if you don't put anything else on the drawing, that note alone tells manufacturers and inspectors that they have to respect the form of the feature according to its size tolerance. A feature cannot surpass its envelope. So I put these little 2 examples here. The envelope is here. That's the MMC limits dimension. And when it's approaching the LMC, it can curl or bend within the envelope. That's totally acceptable. But when it approaches the MMC, it really can't. There's no space anymore. Okay, and then now the last thing, and you don't see this here, but this says Rule 2. The last thing we'll discuss today is Rule 2, otherwise known as regardless of feature of size, or RFS. RFS is really easy to understand. It's so easy, in fact, you might have already assumed it to be the case. It states that the geometric tolerance applies regardless of the size of the feature of size. So no matter if you set the part at LMC or MMC or anywhere in between, you will always have a straightness tolerance of 0.03 millimeters. Okay, well, you might then ask, if that has to be a rule, it must mean we can change this behavior? And the answer is yes. It is actually really common to do so with modifiers. Why would we want to change this behavior? Without going into too much detail, we might, for example, want to add a little bit more flexibility for manufacturing. And this is probably the most common reason to change this behavior, as RFS is pretty strict for manufacturing, that is. So if you see a symbol with an M in a circle or even an L in a circle, that's a modifier changing this behavior. But for now, we're going to keep things as simple as possible and assume that this is not the case. RFS always applies, at least in the examples in here. And that is until indicated otherwise. And that's it. That's all for this video. In the next video, we'll likely go into basic dimensions and certain characteristics that interact with basic dimensions. Thank you very much. And as usual, here are my sources.